What is modulation transfer function? The modulation transfer function (MTF) is a measure of the ability of an optical system to transfer various levels of detail from object to image. It also measured in terms of contrast degrees of gray or of modulation produced for a perfect source of that detail level. Transfer functions are found in circumstances where a response output is related to an input. Examples of systems that can be characterized by a response function are audio equipment, mechanical vibration isolation structures, and seismometers. The optical transfer function (OT) describes the response of optical systems to known input and consists of two components. The MTF is the magnitude of the OT, and the phase transfer function (TF) is the phase component. Next is noise. What is noise? Noise in computed tomography is an unwanted change in pixel values in an otherwise homogeneous image. Often noise is defined loosely as the grainy appearance on cross-sectional imaging. More often than not, the size quantum model. Noise in CT is measured via the signal-to-noise ratio (SNR). Comparing the level of desired signal photons to the level of background noise pixels deviating from normal. The higher the ratio, the less noise is present in the image. Noise in a cross-sectional image will equal a decrease in the picture quality and inadvertently will hinder the contrast resolution. Masthead MAS, or the dose of a CT scan, has a direct relationship with the number of photons utilized in the examination. A useful relationship to keep in mind is increasing the dose of the scan will decrease the amount of noise and hence improve the contrast resolution of the image. However, it comes at a cost, and balancing the dose with the contrast resolution required for interpretation must be considered when determining examination settings. Studies that rely on superior contrast resolution will inescapably require a higher dose than examinations that can tolerate a higher amount of noise. A variety of metrics are used to measure different qualities of CT noise. Noise has many aspects, including magnitude, texture, and non-uniformity. Noise magnitude is quantified simply by the standard deviation. CT noise magnitude makes up the denominator of the signal-to-noise ratio. Noise texture is the visual impression or quality of noise. It can be measured quantitatively by computing the noise power spectrum. Noise non-uniformity is caused by variation in noise magnitude or texture across the image. What is exposure latitude? It is the extent to which a light-sensitive material can be overexposed or underexposed and still achieve an acceptable result. This measure is used for digital and analog processes, for example, optical microlithography or photography. In the case of optical microlithography, this value statistically describes the response of a photoresist to radiation and defines the process window where the photolithographic process can vary within. For example, how well it compensates for spatial non-uniformities of the illumination. In the case of photography, an artistic case, the measurement of exposure latitude is, by definition, dependent on both personal aesthetics and artistic intentions, somewhat subjective. However, the relative differences between media are generally agreed upon. Reversal film tends to have very little latitude, while color negative film has considerably more. It is not to be confused with dynamic range, the range of light intensities a medium can capture simultaneously. A recording medium with greater dynamic range will be able to record more details in the dark and light areas of a picture. Latitude depends on dynamic range. If the same scene can be recorded using less than the full brightness range available to the medium, the exposure can be shifted along the range without losing information in the shadows or highlights. Greater exposure latitude allows one to compensate for errors in exposure while retaining quality. What is detective quantum efficiency? It is one of the fundamental physical variables related to image quality in radiography and refers to the efficiency of a detector in converting incident X-ray energy into an image signal. The words quantum efficiency have a precise meaning. It measures the quantum efficiency of an equivalent virtual detector which produces at its output the same SNR of the real detector even when the input signal is the same. The J is generally defined by the ratio of the squared output signal to noise ratio SNR to the squared input signal to noise ratio SNR2 of the imaging detector. T is dependent on radiation exposure, spatial frequency, MTF, and detector material. The quality, voltage, and current of the radiation applied is also an important influence on T. The ideal detector would have a T of 100% at all spatial frequencies, meaning that all the radiation energy is absorbed and converted into image information.